In this video, we're going to learn how to algebraically and graphically evaluate limits. The first method of evaluating limits, and by far the most used one, is called direct substitution. But before we can talk about direct substitution, we have to briefly visit the concept of continuity. Continuity will be explored more mathematically rigorously in a future video, but for now, all you have to know is a continuous curve can be drawn without lifting your pencil. And that's important to know because direct substitution only works on continuous regions of curves. Now that we've got that out of the way, direct substitution is exactly as it sounds. You directly substitute your approaching value into your function. So for example, here, we're going to directly substitute 2 into x. So this becomes 2 times 2 plus 7, which is 11. And exactly the same here, we're going to directly substitute pi into sine of x. So we have sine of pi, which is 0. That's how you evaluate limits via direct substitution. Pretty easy, right? And this works because on a continuous curve, the y value that you're approaching is just the y value at that point. Okay, so for example, this is a continuous curve. I drew it without lifting my pencil. If I want to find the limit here, it's just the function value here because it's continuous. And as a counterexample, if we have a non-continuous curve, see how I had to lift my Sharpie to place the jump here. If we tried direct substitution, we would get this value, which is incorrect, and the limit is actually this value. So again, direct substitution only works on continuous regions of curves. But eventually, you'll get to a problem where direct substitution will fail. So when I tried direct substituting minus 3 into our function here, I got 0 over 0. And some new vocabulary. This, along with infinity over infinity, is called an indeterminate form because this does not tell us anything about the result of our limit. And if you get this, might be a hint that at this point, the function is not continuous. You should know that the end goal of every limit problem is to direct substitute. So we have to reduce this into a form where direct substitution works. And a way we can do that is factoring. Notice we can factor the numerator into x plus 3 and x minus 2. Like so. And now look, we can cancel the x plus 3's just to leave the limit as x goes to minus 3 of x minus 2. And when we direct substitute here, we get minus 3 minus 2, which is negative 5. This is one of the many ways that we can manipulate limits so we can direct substitute. Another common scenario you might encounter is when you have to rationalize our function. Notice how when I direct substituted 0 into our function, I got another indeterminate form. This tells us that we need to do something more to be able to direct substitute, and that is rationalizing. Remember this difference of squares formula, a squared minus b squared breaks down into a plus b and a minus b. So if you look in the top here, we already have a minus b going on if we let a equal square root of x plus 1 and let b equal 1. So we're going to try multiplying the top and bottom by the conjugate, or a plus b over a plus b, and see what we get. Like so. And notice that I haven't actually changed the limit, because if I don't do anything, these will cancel because they're 1 over 1, and we'll have our original limit. Now we have a minus b times a plus b on the top, so we'll get a squared minus b squared on our numerator. So a squared is square root of x plus 1 squared, which is x plus 1, minus our b squared is 1 squared, so it's 1. And then our denominator is just x times this, like so. And notice that this plus 1 and minus 1 cancel. And we can also cancel this x on the top with the x on the bottom, like so. Now when we direct substitute, we get 1 over the square root of 1 plus 1, which is 1 over 2, or 1/2. And this is called rationalizing because we're getting rid of the radical on the numerator if we multiply by the conjugate. Rationalizing and factoring are the two most common techniques you'll have to use to get to a place where we can direct substitute. But after you learn L'Hopital's rule in chapter 3, you're never going to use them again. On exams, you might be given something like this, where you're given a graph instead of a function and asked to find the limit. So how you go about doing this is I would start some distance away from 1, equal on both sides, and then I would follow the curve with my hands until I got to 1. And that's the limit of the function, which in this case is 4. Or in this particular case, you could argue that since the function is continuous, the limit is just the function value, which is 4. But imagine you had this graph instead, where the point just jumped up to y equals 8. So is the limit 8 now? No, because you're approaching 1. You're not getting to 1. So as far as you know, this curve still continues like this, and the limit here is still 4 because that's what you're approaching. Now the actual value of it is 8, but we don't care about that for the limit. A very important thing to know is that the limit and the function value do not influence each other. Or in other words, we don't care about the actual value of the function at a point if we're finding the limit. We only care about what the function approaches. Now that you've figured out how to evaluate some limits, let's go over their more general properties. The first property is if I'm taking the limit of a sum or difference of functions, then I can break this into two separate limits and evaluate them accordingly. The second property is that if we have a constant times a function, we can just pull the constant out of the function and evaluate the limit normally, like this. And the third one says that the limit of a product is equal to the product of the limits. And finally, the last property is if you have a limit of a quotient, then that's equal to the quotient of the limits. These are the four most important limit properties that you should know, and 95% of limits can be solved using these rules. To close the video, I'm going to end with examples of everything that we've covered in the video. So first, we're asked to find the limit as x goes to 0 of x squared minus 3x plus 10. We could separate this into three limits and evaluate each one independently, but we know that this overall graph is a parabola, and parabolas are always continuous, so we know we can just direct substitute. So this becomes 0 squared minus 3 times 0 plus 10, which is just 10. That's our answer. For our second one, I'm going to first go ahead and try direct substitution. When I tried direct substitution, I got an indeterminate form, which means we have to do a little bit more work before we can do direct substitution. First, I'm going to notice that this bottom is a difference of squares, so we can factor it into a plus b times a minus b, like so. And on the top, we're going to notice that we can factor this into x minus 4 times x minus 1. And now we can see that the x minus 4's cancel just to leave x minus 1 over x plus 4. That just leaves the limit as x goes to 4 of x minus 1 over x plus 4. Now we know that the limit of a quotient is equal to the quotient of the limits, so we can write this. And we know that both of these are lines, and lines are continuous, so we can do direct substitution. When I direct substitute, I get 4 minus 1 over 4 plus 4, which is just 3 over 8. And that's our answer. And finally, we have a graphical question this time. So first, we're asked to find the limit as x goes to c of this graph. So what I'm going to do is I'm going to go to either side of c on the graph, and then I'm going to follow the curve until we get to x equals c. And here we see that this approaches L. So we're going to say that the limit as x goes to c of this curve is L. Now what about the limit as x goes to d of f of x? We see that the function value at x equals d is L. But remember that we don't care about the function value when we're evaluating the limit. Instead, what we're going to do is we're going to go to the graph, we're going to go to either side of d, and then follow the curve until we get to x equals d. And now we see that the limit here is actually k. Just remember not to get tripped up by these holes in graphical limit questions. And that's how you evaluate a limit.